This is a Tech Talk on Brakes presented by Essex Parts. I'm Jordan Bogue, I'm our technical director, and we're going to go through some things. And today we're going to focus on the difference between OE style single piece rotors and a true racing two-piece iron disc. Before we get started, a little bit about Essex. We were established in 1981 in Essex, Connecticut, where the name comes from, as Essex Racing. Essex Racing then moved to Atlanta, Georgia, which at the time was more of a motorsports center, and that was in 1983. During this time, Essex was also an avid participant in SCCA and IMSA organized racing. Essex actually won the lights class in the 1988 24 Hours of Daytona. These are the prototype cars that they ran in that class at the time. And then in 1992, Essex Parts Services, which is what it is now, was created. And then in 2004, we moved to our current location in Charlotte to be closer to our NASCAR clientele and some of our road racing clientele that's up there. And then during this move to Charlotte, we brought more engineering in-house and developed and built a brake dyno. And this brake dyno has allowed us to become kind of the standard for racing friction performance characteristics. And we do testing for all types of race series in the US, IndyCar, NASCAR, IMSA, you name it, we've done testing for them. So a little overview of what we're going to talk about. We're going to talk about iron composition. Iron is iron, right? It's not always that simple. And then we're going to talk about vane styles and how they affect your cooling. And then we're going to talk about attachment, of course, a floating style disc versus a bolted two-piece versus a fixed OE style single-piece disc. And then we're going to talk about different faces. I know that drilled faces have been very popular for a long time. They look cool, they look fast. Well, they may not always be the best. So we're going to talk about the differences there. And then at the very end, we'll talk about a proper warm-up procedure for a true racing disc. So composition, iron is iron, right? Well, iron, like anything, can be tuned to its use case. And so in the case of racing brake discs or a road brake disc, those are two very different use cases. So road brake disc, they're prioritizing wear, they're prioritizing squeal, they're prioritizing manufacturability, they're prioritizing how much it's going to cost. Those are very important things to them. Racing brake discs, cost is not as big of a deal. Durability is still a big deal, but it's durability in a different way. We're looking at durability at high temperature and high stress. And then as far as squeal, of course, we don't care about that. Performance is everything. And so the most common choice for racing iron is a slight variation of the SAE J431 standard. That's typical for automotive brake discs. And I've blocked out the exact percentages, but you can see kind of the different materials that are in it. And it's all how you bake the same cake in a slightly different way. So the main components, the main additives that you can get to get different characteristics out of a brake disc are carbon, manganese, phosphorus, sulfur, silicon, copper, chromium, and then another one is molybdenum. But that's very, very high tier, mostly only used in NASCAR and GT racing. But the copper and the manganese content specifically I want to call out because those two are definitely two that are different from a road car to a racing disc. Copper and the manganese change how effective a disc is at transferring energy through the core of the disc. Copper is very conductive, we all know that. So you add copper to the disc, and that copper accelerates how fast it takes the energy that you're generating on the friction face and takes it through to the core. And the more even your temperature distribution is, the less likely you are to crack a disc, and the more consistent the disc is going to be. And as far as the microstructure goes, you can see in the top left, that's a picture of about 1,000 times magnified of a brake disc. And those ferritic iron islands and carbides are things that you don't want. And the type A graphite flakes are what you do want. The ferritic islands and the carbides are going to create weak spots in the iron. They're almost like voids, but it's not really a void. And those you get different quantities of depending on how fast you cool a disc. And so that goes back into the cost effectiveness that OE single piece discs, they're pumping them out, they're letting them cool for maybe a short amount of time and then shipping them out to get put on a car. Versus a racing iron, once it's cast, it's cooled in a very controlled environment. It's very particular on how it's cooled, at what temperature steps it goes through, and then it's machined, and then it's stress relieved again at temperature, and then it's sent out to be put on a car. Vane styles and effective cooling. So there are three main types of vanes that you'll see. There's up here on the top right, pillar vanes, straight radial, and curved radial. These are important because your disc is effectively acting as a fan. So I've got this little animation here of a centripetal style fan, and that's exactly what your brake disc is. So it does whatever it can do with air in the center and then pumping it out the top. And in order of increasing effectiveness, it's pillars, straight radial, curved radial. The way the curved radial, you can think of air as a fluid or air as a particle, and the curved radial vanes help accelerate the air out of the disc, which ultimately means that you're getting more airflow through the disc at a time for a particular speed. So now we are pretty confident we want curved radial vanes. Well, how many vanes do we want? If to a point, increasing the vane count increases your airflow, as long as you can thin the vanes while you increase the count. So that's one of the things that AP does really well, is that they've got advanced manufacturing to the point that they can get a 60 vanes in a 299 millimeter disc without compromising the actual gap between the vanes. They continue to thin out the vanes, not compromising disc strength, and still increasing the throughput that air can get. So be wary if you see a disc that's a very high vane count. Sometimes they're not actually shrinking the vane between their, say, 48 vane and 60 vane. And if they don't shrink the vane, then you shrink the amount of area that you actually have to flow air. So that's something to keep an eye on. Is more cooling always better? That depends. If you're increasing cooling at the expense of thermal capacity, then it's not always better. And I say thermal capacity in the sense of how thick are the faces, how much mass is there in the disc, because the mass of the disc is your biggest influence as far as what is the actual equilibrium temperature of the system going to be. How much energy can it actually take? Which I'll talk a little bit more in a second. So more effective cooling as far as what you can do to aid the disc. So the disc is your air pump. Now, how do you get more cooling? You supply more air to the air pump. And so the top right here, I've got an example of a suboptimal cooling system. So these corrugated pipes are really, really popular. And they're good in some cases, but they have a couple problems. Number one is that they're really rough. So that's creating turbulence inside that hose, and it's going to restrict how much airflow you can actually get through it. Number two is that you've got some pinch points along here. And if it's not done well, and especially at steering lock, you can start to crimp that tube, and then it just slowly starts to close down on the control volume and how much air it can actually move through it. And then the third and biggest thing is that it's dumping directly out onto the inboard side of the disc. When you're putting a lot of air directly on one face of the disc, you're cooling the disc unevenly. And when that happens, you end up with that side of the disc running 200, 300 degrees cooler, and the outside of the disc trying to expand as it gets hotter, and then that can cause a lot of cracking. So an effective cooling option, of course, this is an F1 corner, and you can see they're pulling air from a really high pressure area, so a high volume area, and they're wrapping that as quickly and as smoothly as possible into the center of the disc and across the top of the caliper. Now, obviously, we don't all have F1 setups, but the next best setup that we've seen and that we've done testing with is just a simple diverter on the control arm, taking air and pushing it towards the center of the disc, and then you allow the air pump to do what it's best at, which is pumping air. A lot of people really overthink the cooling side of it. All you need is a simple straight shot from the front bumper to the inner fender well, put air in there, and then have a little deflector or something to send it towards the center of the wheel, and that's going to be all you'll ever need. All right, now more into the floating racing disc versus the single pieced or bolted disc. So everything expands when it gets hot. It's just a matter of how much. And so iron has a thermal expansion coefficient of 0.06 of a thousandth of an inch per inch the sample is wide times how hot it is. So what that breaks down to is that a 380 millimeter disc, which is a very common disc size on a racing disc, when you get it up to 1400, 1500 degrees, it's going to expand by about 1.5 millimeters, so about 60 thousandths, which seems small, but in the case of say a fixed bell disc, where one side of that bell is restricted and can't expand, that turns into a lot of stress. And that's what this calculation is here, is this shows a free sample available to expand. It's going to do fine. It's going to expand a prescribed amount. As long as you know what that amount is, you're okay. Well, this represents the other side of the disc, the inboard face, that's constrained. Well, when it's constrained and it's trying to expand, that's putting a lot of force and a lot of stress into the disc, which will ultimately lead to the disc turning into a potato chip or cracking, whichever one comes first. So any disc that's going to operate at high temperatures needs to be a floating disc. OE single piece discs are just not meant for that. They're meant for panic stops on the interstate and just regular driving. They'll never see over 500 degrees consistent. Versus a racing disc might, once it gets warmed up, might stay 1,000 to 1,300 degrees the whole event, the whole time on track. And then bolted discs are slightly better than a fixed bell disc because the hat and the iron are able to expand at slightly different rates. The aluminum has a higher coefficient of expansion, so it's going to expand a little bit more than the iron bell will, making up for the fact that it's constrained, but it's still not the most optimal as far as what you want on track. And those are usually, as far as what we offer, we only offer those on lower horsepower applications because they're not seeing as much temperature. Then we've got face features: plain face, drilled, and slotted. The common misconception is that drilled faces are needed because pads outgas. Well, pads haven't outgassed in about 30 years. Old pad technology using organic compounds, they had a lot of outgassing from that organic compound burning off. Most all common race pads anymore, especially what we carry, is all inorganic binders, and they burn, deteriorate, whatever you want to call it, as you run with little to no off-gassing. The groove faces are very important because they help promote an even transfer layer across the disc. And by transfer layer, I'm talking about you're taking the pad material that's cut off as that edge comes by, and then you're gently smearing it across the face of the disc. This works well for two reasons. One, your friction in the system comes from the pad material against the pad material that has been deposited onto the disc. That's where you get the most friction from, is the pad on transfer layer. Pad on iron is going to be about 10 to 20% less, like when you first go out and you go to bed in the brakes and you feel like it really hasn't come to life yet. That's what you're feeling there. And then the other reason you don't want holes is a hole is a stress riser. So stress is kind of like fluid flow, that when you send water down a channel and then suddenly you put a stop in the middle of the channel, you're having to put more water through a smaller area. It doesn't like it. Same thing with stress, that if you have that hole, all the braking torque that you're generating is having to go through a cross section that has less material now. So you're going to be more likely to crack, especially towards the edges on a disc that has drilled faces. Right? And slots, as far as evacuating water, evacuating foreign debris, they work just fine. About a 20,000 steep slot is all you're really looking for. And then a proper warm-up. So this is an example of a graph from a test that I ran on our dyno in-house. And you can see that these are small stops as I'm warming the disc up because I want to make sure not to crack it. And then we go into bigger stops. And then as you get up to the top, you can see it starts to reach what we call equilibrium. The disc has reached its balance point from the energy that I was putting in, the time space between events, and how much energy it can evacuate based on the airflow that it was pulling. So until you get towards that equilibrium temperature, you want to be careful about how big the energy events you're putting into the disc are. Otherwise, you could end up cracking, heat check cracking the disc. And the reason this happens is because racing brake discs are the perfect balance, or strive to be the perfect balance, of durability versus weight. Because we can give you a disc that won't crack under any circumstances, but then that disc is going to be effectively a dump truck disc, and it's going to weigh 35 pounds, and everybody's going to be unhappy about the unsprung weight and the rotating mass. So the difficult part is designing and developing a disc that can handle 1,000 horsepower, but is also still lower on rotating mass and inertia than OE options or other things that are available. Because ultimately, at the end of the day, everybody wants to go fast. People want to stop consistently, but everybody wants to be faster, stronger. And to do that, you have to really walk that line of being durable enough to get good life out of the disc, but also being light enough that you don't kill performance on the car.